No problem. First of all, welcome to the lab. We hope we had a nice morning. Prepared the slides yesterday, a couple of days ago. They put a lot of chemistry. So I don't think maybe you are the right audience to talk about really too much about chemistry, but I want to talk about the big problem, right? Plastic. Everyone can understand plastic accumulation. We start to talk about quantum computing. Who knows the physics behind quantum computing? Very few people. I still don't understand completely how a quantum computer works, but I can understand if I see a straw on a beautiful beach in the Caribbean, saying something is wrong, right? And today I want to talk about a little bit what we are doing at the lab, but also as an entire complex, not just at Argonne. This is a really there was a huge investment for both applied basic science to really understand how can we design new plastics that are recyclable by design. How can we maybe one day go in the landfill and do urban mining? Let's say maybe in 50 years there is no more oil, but we need fuel. Maybe we're going in the landfill and we start to dig and recover all the plastics that we have in the landfill that we thrown away in the past 70, 80 years. One thing that is very, very important, we need to change our way of how we're thinking. Plastic maybe is not the problem, maybe plastic is the solution, right? We want to use this plastic as an opportunity, for example, to create jobs, to create new economy, to create valuable product that maybe we don't make, but maybe plastic is the right way to make it. And in fact, I think later you're going to talk with a company called Eternal Upcycling. They were Ryan and Robert were two of my students that started the project with me, and they thought there was an opportunity, economic opportunity, and they started their own company, and the lab, Argonne particularly, is licensed patents that we developed in these 12, 6 years, and they are trying to make money. This is good because it was a taxpayer money that we used to start this project. But we talk about plastic. Plastic is a global issue, right? It is a map. Probably you heard about the patches. The most famous is the one between Asia and United States, the number one. It's a floating 1 foot depth of plastic, plastic that's floating in the ocean. This is almost 80,000 tons of plastics, and it's 2 times the size of Texas. Think about how Texas is big. We have 2 sizes of Texas that is floating in the ocean. Unfortunately, that is not the only one. We have other. Every time there is a current in the ocean, we have 5 patches. I'm from Chicago. I'm Italian born and raised, as you can hear from my accent, but I live downtown, and plastic is also a problem in the lakes, correct, from the fishing. And the chemistry and the flow and the current that we have in the ocean is different in the lakes, correct? We have 2 different ways of plastic and degrade in the water. But this is why we're doing research, correct? We have 2 sides of Texas, 1 foot deep, that is floating in the ocean. There. What we are interested in really to create, as I mentioned before, an economy based on waste. And because if you create an economy based on waste, we can really start to think about a net zero carbon cycle, where every carbon that is already in the atmosphere can be waste, can be CO2, can be methane, everything that is already out from the ground should be recycled so many times, in theory, infinite number of times. And plastic, of course, is part of the solution to really close the carbon cycle. I work at National Lab. We care about numbers, and we care about oil, correct? Energy. Let's start to think about energy. We produce 8.3 billion tons of plastic every year. Every year, worldwide, 8.3 billion. And roughly correspond 6 to 8% of the total crude oil that has been extracted annually. 8% of all the oil that we dig from the ground has been transformed in plastics. Of this 8.3 billion, 75% goes to the landfill. And this is worldwide. That means only 25% of the total plastic that produced every year stays in that cycle that we talk about. If you think about the municipal waste, well, everything you put in your, I don't know where you live, but I live downtown, we have two bins, the black bin and the blue bin. The black bin is roughly 10% of made of plastics. This is very bad for us, for the United States. 5% is what we are doing in recycling. We could do much better. We don't need that. And 55% of the total plastic produced is polyolefins. Plastic bag, films, water jug, shampoo containers that are called hydrocarbons. And the total waste equivalent is 1.3 billion barrels of oil. This number, this 1.3 billion of oil every year goes to the landfill. Think about how much you pay for your gas. $4 each cargo. Imagine if we can recycle all of this oil instead to store this one in the landfill. We can transform it back, for example, in fuel or chemicals that can be used on your day hikes. This is the fate of plastics. We talk about the 8.3 billion. 70% to almost 80% goes to the landfill. And this is 10%. This is worldwide. Correct? This is not United States. Correct. Only 9% of the total plastic produced is still in the carbon cycle. And do you know what is the problem? The problem is here. If you see the symbol, correct? Oh, it's a symbol that means it's recycling. It's not. Only 1 and 2 are recycling. The polyethylene terephthalate, plastic bottle, is 100% recyclable infinite number of times. If we are doing an efficient collection, we can recycle this bottle to make a new bottle infinite number of times. High-density polyethylene, water jug, milk jug, shampoo bottle. We can use it, but not for the same application. I cannot, for example, take a water jug to a water jug, because during the mechanical recycling, that plastic is losing some of the mechanical and thermal properties, and then when we're losing properties that are very, very important, for example, to conserve the food that is inside of the water, and that water jug became a rug. This rug probably is made of plastic waste. And if you go to any of the playgrounds, all the playgrounds are made of plastic waste. That means we do in the first case, we do 100% recycling, correct? We go from a plastic bottle to a plastic bottle, recycling. In the HDPE, we do the downcycling. We go from something that is very valuable, water jug, that conserve our water, to make a rug. But after the rug, end of life of the rug, also the rug goes to the landfill. There is no other way to recycle the 3 to 7, right now, most of this goes to the landfill. Even if there is a symbol that means recycling. There are some new technologies, particularly for polypropylene, that are coming out on the market right now that is very, very interesting. The worst is polyvinyl chloride, the piping, correct? That 100% goes to the landfill. No one wants to deal with PVCs. It has a very, very important properties. For example, in IV bags, all the pharmaceutical, all the medical are made of PVC. That means every year they generate tons of this material that is very, very important, but we need to develop new technology to deal with this material. The most common mistake is the styrofoam. This is not recyclable, and my neighbor put styrofoam in my blue bin. Now that blue bin became completely recyclable. When they see a styrofoam, everything goes to the landfill. Even if the other 99.99% was clean, pure PET, pure HDP. Now we contaminated the blue bin. For that reason, we really need to, in fact, the plastic problem most of the time is really teaching problem. We need to educate the community how to do an efficient recycling approach. Don't put styrofoam in your blue bin. Correct? Don't put polypropylene in your blue bin. Don't put polyvinyl chloride in your blue bin. And we started this project almost 10 years ago, that no one was talking about plastic recycling, because I was interested in visiting one of the material recycling facilities. If you drove from Chicago to the lab, at some point after Midway on the right side, you see these facilities. And in Chicago there are three, roughly 3-4. Each of them serve 3-4 billion people. And this is where your blue bin lands, correct? You can see the truck full of waste from blue bin collection. There is a separation, and aluminum and paper are very easy to separate. These are 100% recyclable, and they are doing separation because the facilities is making money in selling these two materials, correct? They get paid from someone to come to pick them up and bake. But then the story became very sad when I visited the plastic separation. Okay, this is PET. Okay, this PET, this is 24/7, 365 days a year. This is the speed of, there's a belt, there's a plastic bottle with a particular piece of this PET. Was in the chemical structure of the plastic, there is something that is a sensor at the end that can recognize the plastic bottle, and there is a jet of air that is pushing away the plastic bottle. Do you see why we don't want bags or films in your blue bin? Because if there is a film of a plastic bag, now, come on. Now the plastic bag is flying away with the PET, and now the PET is contaminated with the plastic bag, and now became a recycling. Oops. The next one is.
All right.
Next one is the water jug. There is a robot. There's myself taking you. See, there is a milk jug, and there is a robot to recognize the sensor with an arm that recognize the water jug, picks the water jug, and move it mechanically on a different bin. But take a look at that. See, there was a water jug, and the arm didn't recognize it, it missed it. That means we lose some material during storage. And this is when I start to talk with my group. I say we need to work on plastic recycling. 2016. That is how we do separation for the rest. There are 6 hours every day, 6 hours times 4, 365 days a year. This is what I said. Got it? Just want to reassure you again, and everything goes to the net. And you can, going back to the connection between quantum computing and plastic recycling, you see right away what is the problem. Problems here. And also at our household, that we don't know. Most of the time we don't know how to do recycling at all. This is the technology, a little bit of chemistry, this is some technology called, for the PET, this is called meta-analysis. We can deconstruct this plastic back to the monomer, and then we can repolymerize multiple times. There is some new technology for styrofoam in Europe, the United States. US is really invested in pyrolysis, called chemical recycling. The EPA is suing companies in California for that, because it's misleading, like the symbol, correct? But that is a way that we can take, for example, plastic waste, make an oil that will look like an oil, and then blend it with the crude oil, and restart in the process to make chemicals. And in some part of the country, we burn it to produce electricity. That is the one is from Iowa. That is the Ames plant. They are burning plastic to produce energy. That could be also a possible solution. A little bit what we are doing in my group, the thing called upcycling. Corinne we talked about before, about mining. We want to go in the landfill and recover as much as plastic as possible and divert plastic waste from the landfill. And we want to use, in my case, catalysis or material to convert plastic waste, for example, in oil. We can make new polymers from old polymers. We can make surfactants. We can use, for example, as a detergent or in cosmetics. And what we really want to do is upcycle. Like we talk about recycling, downcycling. We want to take plastic waste and make something that is more valuable than the plastic waste. Maybe too much chemistry here, but I think you saw this. These are real data that you saw in the bridge report for the students to use to prepare the plant. But the idea is we want to take plastic film, we want to make a liquid that is a very, very nanopermeable dispersion. That is, instead to have a large, let's say you have in this curve, each at this point there is a molecule. Each of these points is a molecule. What we want to make in a single chain instead of 1,000 chains. Because if we are a single chain, I can use to do new chemistry. In fact, one of the liquids that we are making of oil, called tribological oil, base oil, imagine one day you go to Jiffy Lube, change your oil, and 50% of your synthetic oil comes from plastic. Instead of to dig the ground and purify the oil from it. And this is what you're going to provide later. This is the company. And now they are in the process of building a power plant. We want to show that this technology is valuable for the market. The other thing that we are dealing in my group is, can we make the plastic bag that is unrecyclable because of the landfill? Can I make, for example, a polymer or new polymers that have the same properties of the polymer but is 100% recyclable? And that is a very, very big challenge. Where it's not about success, it's not ready for commercialization, but we have already proof of concept. And the idea, for example, I can take a water jar or a FedEx envelope. When I saw the FedEx envelope the first time, I thought it was paper. Because if you take a look very closely, they have these fibers, but it's not paper. It's long chain of high-density polyethylene. In fact, if you try to wrap it, it's impossible to wrap it. It's so strong, but we show that we can take, for example, a FedEx envelope, and we do some chemistry, and we are able, for example, to make a new polymer that has the same mechanical and thermal properties of the bag, but now is 100% recyclable. And in fact became also biodegradable under some conditions. And this show, for example, the green one is that HB, the envelope, and this is the meat product. This is how much I can strain, I can pull the polymer without breaking it. Now we have the same polymer, same properties, but it's recyclable like water now. And I think we're already late. But yeah, this is the two examples that I shared today. One is plastic to motor oil, for example, or I can take a water jug to make a water jug, but it's 100% recycled. And of course, I didn't do anything by myself. There's a lot of people involved. This is a big investment. This is my group here at Argonne, and we are part of a bigger institute on plastic upcycling that's supported by the Office of Science. And I think there is a lot of people involved, and this is the key. You need to have people with different background and different skills sit at the table. You want to have economists sit at the table, you want to have physicists, we want to have material scientists, we want to have engineering. This is a problem that we really solve with a lot of people in the same room talking. And I'm happy to take any questions. If you want to talk about quantum computer, we can also talk about quantum computer. I'm not talk about plastic. Yeah.
So I just wonder if you have an idea of in terms of scaling, if some of the research what you're working on is like plastics to motor oil, for example, doesn't that feel a little bit like we're kicking the can down the road if we're talking about future trying to move to electric vehicles that don't need that oil? And I'm sure there will still be engines that need it in terms of gas turbine, but is it going to be millions of gallons of recycled oil for, is it a match what the need is going to be, or if we just kick we can down the road?
Yes and no. Yeah, we kick a little bit, but I think of the oil, technological oil, that are 100% recyclable. You can rectify it and reuse them. You can have time. EVs as also lubricants, or the engine or the parts that are rotating to this lubricant that are different from this kind of oil. But one of the projects we have, we're working to develop waxes that can be used for EVs. Also the batteries, you need to cool it down, and there is an oil to cool down, because oil are very good to dissipate heat, and they are using that. There is a lot of application, for example, and we have a project where we're testing now in the field. We're using this oil for lubricant in women. That could be another. You're right. For lubricants, it's limited, but the nice thing that we have one technology can also that you need other different technology that target different part of the pie of the carbon circularity. And in fact, the ultimate goal is really to develop CO2 to polyethylene, correct? Because you use the polyethylene, you burn it, you recover the energy, you recover the CO2, you transform the CO2 back in the polyethylene. But that is high energy, it's very intensive process.
Do you think it's possible that one day we can make a polymer that could break down in a very short period of time, like
Yeah, maybe. We already do that, correct? If you think about PLA, polylactic acid, coming from corn in cornstarch, or biomass, it's great. However, it doesn't have the same mechanical properties of the plastic bag. Classic example, I can take a HDP glass, water glass, and put it in my dishwasher, and I wash it, and nothing changes. If you take a PLA, polylactic acid glass, you put it in your dishwasher, there is no PLA at the end. Everything melted. Because the mechanical and thermal properties are not good enough to survive rewashing and yes, there are opportunities to really develop new polymers that are recyclable by design with the same mechanical and thermal properties of existing plastics. However, you have to think about economics. Everything is about economics, correct? A plastic bag costs probably 1 cent to make it. To make maybe a new plastic bag made of a new polymer can cost $10. Are you ready to pay $10 for a plastic bag? I mean, there is also stuff to think about how the population are going to support it. That was always the balance between economic and science.
I feel like that's a short-sighted approach to looking at it. not you, I'm not saying you, but the economics of it, because there's so much cost to collecting bags in the city. Like in the city of Los Angeles, where I'm from, we pay $80. I think it's $80 a person, and there's 11 million people to collect bags every year. So that's a cost to the city. So if we're thinking about the cost of like it's $10 a bag, we're just looking at that and that
Yeah,
perspective.
I was thinking more about the capital investment from the oil companies.
Well, that's another
We're
issue.
talking about $1 trillion of capex investment of building. I mean, we just opened 3 new ethylene cracker, one in Louisiana, one in Pennsylvania, and their life is 50 years before the companies start to recover really the cost of that investment. It's really a balance to find everything works at scale, and to make really economical valuable, we have to go at scale. But you're 100% right. The cost of, for that reason, I
We
think,
don't consider external factors when we're looking at costs. And that's the problem.
one thing to solve that is, as I mentioned before, is really education. Why we need 2 bins, the black bin and the blue bin. I'm Italian, my mom has 7 different bins, different colors.
Yeah.
You do, we do, I mean, they do it in Italy and Europe, what we are doing at the MRF.
Yes.
But I'm not here to have to put any policy. This has to be you. I like just saying, these policies, the policymaker. If you want to do it, and the city where she lives, they provide a barcode for the bag. If they open it and they find, for example, aluminum in the glass, fine.
Yep.
But again, this is a policy. I'm not a policymaker. I'm a scientist. I do science.
Thank you for the talk. The striking thing with those videos of the removal of stuff from some sort of separating the trash makes me think of like uniformity, right? So like processing the trash beforehand into the small chips that we saw for the feedstocks, right? Like putting it down into smaller, more uniform chunks. Does that help with like separation of the different types of plastics? I don't know how any of that works, but is there enough property differences within the plastics if you have uniform sized chunks to be able to separate them either optically or whatever you're doing there?
The answer totally is no. Let me show you.
We talk about here.
Okay. Number 2, number 4, number 5 have the same chemical structure. It's just you go from one hydrogen to one methyl group. That's it. And there is not enough diversification separate from a sensing bunker. We're going to do very well with DC, so with the NC number 3, number 1. But also I was talking with
In the production of USO, sorry.
in the separation.
So yes, so in the separation, but if I'm not talking about policy, but if in the preparation of it we only allow plastics that are ionized or given some additive that will allow each of these different ones to be separated by these.
Yeah, it's obviously the cost. Go back to college, the cost of something like that at scale is that safe for alpha. What is the effect of this molecule on the additives that are reaching the water or in food? One thing that talking about the size, and I didn't know after I talked with this guy, when you think about this is their number 1. This is paper, thank God, but sometimes it's a film with number 4, it's in another polyethylene, and this is number 4, polypropylene. And I thought, there are 3 different types of plastic I want to separate. Instead, they prefer to have the cap on the plastic part. because during the mechanical sorting, this is too small and it goes through the filters. Yeah, you don't think about the things, correct?
Yeah.
But there is physical and mechanical problem that, and it's much easier for them. It's much easier to recover this polypropylene from the PET if it is closed in the bottom. No, because this is too small and they're losing during the separation.
Please. Yeah, so I'm wondering about the lifetime and reusability of the catalysts they use for chemical upcycling.
Yeah, this is one of the big problem, correct? I mean, in industry, chemical industry, everything that goes in the reactor the life should be at least 10 years. This is what the company is targeting, correct? They already show that they can recycle the catalyst. It's made of platinum, that is one of the most expensive metal on Earth. But if you recycle in fact, right now we are looking in the first version, we're in a closed system, correct? You run the reaction 24 hours, you open, you recover the catalyst with the liquid, then you close, you put fresh plastics, you close it and you do it. What we are looking right now is can we have a flow system that you never have to open, correct? You go from a batch system to a flow system. And that is when you start to really go at scale and looking at industrial application. But yeah, the cost of the catalyst is very, very important. But when we did the techno-economic analysis, the cost of platinum is included in the final cost of the product. And one of the things that we're looking at lubricants, because a gallon of polyalpha olefin, when you go to change your oil, for synthetic oil is $100, correct? When you change the oil. And if that $100 per gallon of oil for plastic waste, that is cheap, very, very cheap. You can start to use expensive catalyst, expensive method to do it. But yeah,
And the director of this crew, thank you for this great talk.
we're already late.
Thank you for that.